Tesla has just sent shockwaves through the robotics world with an unexpected reveal. Footage of its Optimus Gen 3 humanoid robot running at approximately 5.2 miles per hour. A speed that actually exceeds what Elon Musk himself had previously cited as a safe operational ceiling. What made this clip truly remarkable wasn't just the velocity. The robot demonstrated a genuine airborne phase during its stride, meaning both feet left the ground simultaneously. That characteristic, known as a true running gait, is something only a tiny number of advanced bipedal machines in existence have ever managed to pull off. But Tesla didn't stop there. The company also unveiled a next-generation robotic hand engineered with somewhere between 22 and 24 degrees of freedom, alongside an entirely AI-driven simulation platform designed to generate hyper-realistic virtual environments where robots can be trained before they ever touch the real world. According to Elon Musk, this showcase represents the final public demonstration of the Gen 3 platform before its commercial debut arrives next year. So what exactly are the 5 biggest leaps forward that define this new generation of Tesla's humanoid robot? And why does Musk remain so bullish that Optimus will ultimately eclipse Tesla's electric vehicle business in value? Let's break it all down. One of the things that sets Tesla apart in the humanoid robotics space is how openly it shares performance data. Robotics analyst Dr. Scott Walter has noted that most companies in this field are deliberately vague about their machines' real-world speeds and capabilities, largely to avoid uncomfortable side-by-side comparisons with rivals. Tesla has taken the opposite approach entirely, releasing unedited footage, providing frame-by-frame speed calculations, and inviting outside experts to verify the numbers independently. In a field where marketing often outpaces reality, that level of transparency is genuinely unusual. The Locomotion breakthrough deserves particular attention. Independent analysis of the running footage confirmed that Optimus Gen 2.5 traveled roughly 4 meters in under 2 seconds, translating to approximately 2.34 meters per second or 5.2 miles per hour. The speed itself is notable, but what carries more weight is the mechanical milestone behind it. The robot exhibited an authentic flight phase during the run, a brief window in each stride cycle where neither foot was in contact with the ground. This separates true running from fast walking, and achieving it in a stable, controlled indoor setting puts Optimus in very select company among bipedal platforms globally. This progress matters practically, not just technically. The vast majority of jobs a humanoid robot might realistically perform, moving through warehouses, navigating factory floors, assisting in homes, don't demand sprinting. They require reliable walking, confident navigation around people, and enough speed to be genuinely useful rather than frustratingly slow. Earlier versions of Optimus maxed out somewhere between 1 and 1.2 miles per hour, well below typical human walking pace. Just reaching 2 to 3 miles per hour consistently was considered a minimum viability threshold for many industrial applications. Tesla has now cleared that bar with significant room to spare. Analysts believe this Locomotion jump reflects how deeply Tesla's autonomous driving research is now feeding into its robotics program. The same neural architecture that taught Tesla vehicles to read road environments in real time is being adapted to give Optimus the spatial awareness and dynamic balance it needs to move through unpredictable physical spaces. It's not a coincidence. It's a deliberate transfer of hard-won AI expertise from one domain to another. That said, the demonstration wasn't flawless. Observers noticed that the front section of the robot's foot bent upward noticeably during the run, apparently due to a split-sole construction. While that design choice was intentional, it creates a potential vulnerability in outdoor environments where debris could get lodged in the gap. Dr. Walter anticipates that Tesla will address this with a fully sealed foot design in Gen 3, a sensible refinement as the robot edges closer to real deployment scenarios. The robotic hand Tesla showed off at the same event may have been the most technically jaw-dropping element of the entire presentation. Rather than a simplified gripper or a basic mechanical claw, what Tesla revealed looks and behaves more like an engineering replica of an actual human hand. The device incorporates 22 degrees of freedom, or up to 24 when accounting for subtle micro-movements, driven internally by 17 linear actuators working through a network of tendons and synthetic ligaments. Surrounding the mechanical structure is a flexible outer glove engineered to stretch precisely along each joint's natural fold lines, allowing smooth, fluid movement that tracks closely with how a real hand operates. The tendon groupings are color-coded by function, with separate systems governing flexion, extension, and lateral movement. This organization allows fine-grained force control without requiring a dedicated motor at every single joint. The thumb features its own opposing joint modeled on human anatomy, and the little finger's base knuckle can move independently, a level of mechanical nuance rarely seen outside of advanced research prototypes. The inherent challenge with tendon-driven systems is that they introduce coupling effects. When the wrist rotates, tendon lengths shift, which can cause unintended finger movements as a side effect. In humans, the nervous system corrects for this automatically without conscious thought. In robots, it requires sophisticated software compensation, an ongoing challenge across the entire field of dexterous robotics, not just for Tesla. Musk's team appears confident that algorithmic solutions can manage this, though it remains an active engineering problem. One design issue that reviewers flagged: when the fingers extend fully, a visible gap opens along the top of the knuckle area, placing stress on the glove material. Repeated cycling of this motion could lead to premature wear or tearing over time. Experts expect Tesla to tighten this aspect of the design in the Gen 3 version, potentially adding actuators to support active extension rather than relying entirely on passive tension in the tendons to return the fingers to an open position. Still, taken as a whole, the hand represents a meaningful stride forward in one of the hardest unsolved problems in robotics. Walking is impressive, conversation is impressive, but the ability to manipulate objects, to fold clothing, operate tools, handle fragile items, and perform fine assembly work is ultimately what determines whether a humanoid robot is useful enough to justify its cost. The third major reveal centered on Tesla's neural simulation environment, and in some respects it may be the most consequential development of all three. Unlike conventional simulation platforms that rely on game engines and manually scripted physics, Tesla's system is built entirely on neural networks trained from an enormous corpus of real-world visual data gathered by Tesla's vehicle fleet. The environment it produces isn't coded. It's generated dynamically, frame by frame, by an AI model that has internalized how the physical world actually looks and behaves. A live demonstration showed a person operating a vehicle using physical controls, while the neural model synthesized every element of the visual environment in real time. The implication for robotics is significant. If Tesla can create a simulated world that faithfully mirrors reality, complete with accurate lighting, surface textures, object physics, and spatial relationships, then Optimus can be trained on an enormous range of tasks and edge cases without any wear on physical hardware and without putting humans or property at risk. This mirrors the strategy that accelerated Tesla's full self-driving development, except that applying it to embodied humanoid AI may prove even more powerful, given how much more varied and unpredictable the tasks a robot must learn are compared to highway navigation. On the manufacturing front, signals are accumulating that Tesla is treating Optimus as a genuine industrial priority rather than a research project. Reports from suppliers in China and Canada indicate that quality inspection processes at Tesla facilities are already underway. Giga Texas has reportedly begun allocating dedicated floor space for Optimus production infrastructure. The Fremont factory has been referenced in connection with a potential production capacity of up to 1 million units annually. These aren't the kinds of investments a company makes unless it believes the product is close to ready. Musk has publicly confirmed that the Gen 3 robot will be officially revealed in the second quarter of next year, with March cited as a possible target date. Dr. Walter's read on the situation is that Gen 3 won't be a ground-up redesign, but rather a series of targeted refinements: additional forearm motors, a more stable thumb mechanism, a fully enclosed foot, while the current Gen 2.5 platform continues serving as a live testbed for software development. The idea is to let the AI team train continuously at full speed while hardware engineers work in parallel to finalize the next generation. Pricing remains one of the most actively debated questions surrounding Optimus. Early speculation centered on a $20,000 consumer price point, but analysts increasingly view that figure as unrealistic for the near term. A price closer to $100,000 appears more plausible during the initial commercial phase, with costs declining as manufacturing scales and supply chains mature. Tesla has indicated it will launch a rental program ahead of broad consumer sales, potentially pricing access at around $200 per month. This approach gives Tesla a controlled channel to gather real-world performance data monitor how the robot behaves across diverse environments, and refine its behavior before unleashing it across millions of households. The labor market context surrounding all of this is worth understanding. The United States alone is currently short roughly 300,000 manufacturing workers, with logistics facing a deficit of 600,000 to 700,000 positions. These aren't short-term fluctuations. They reflect structural shifts in workforce availability that are expected to worsen over time. A general-purpose mobile robot capable of performing a wide variety of physical tasks represents a direct response to that gap. If Optimus can reliably handle even a fraction of the work that currently goes understaffed, the economic case for deployment at scale becomes very compelling very quickly. Musk has made sweeping predictions about where this ultimately leads. He has suggested Tesla's valuation could reach $25 trillion on the back of Optimus, and has thrown out figures of 10 to 20 billion units as a potential global demand ceiling. Independent projections are more conservative, but still striking. The humanoid robotics market is expected to reach $38 billion by 2035, and new entrants are entering the space at an accelerating pace. What separates Tesla from most of those competitors, according to Musk, is vertical integration. Tesla designs and manufactures its own actuators, motors, power systems, structural components, and electronics in-house. That gives the company faster iteration cycles, greater quality control, and a cost structure that pure robotics startups cannot easily replicate. Over the longer term, Musk has projected that per-unit production costs could fall as low as $10,000, opening up a future where humanoid robots are as economically accessible as automobiles. Consumer versions are expected to launch in 2026 at initial prices between $20,000 and $30,000, with the rental option preceding that as a softer market entry point. The use cases Musk envisions are deliberately broad: childcare, elder care, education, cooking, household cleaning, grocery shopping, pet care, yard work, companionship. Anything a human being currently does with their time and body, Optimus is theoretically positioned to assist with or take over entirely. The gap between that vision and today's reality remains wide. Current units operate at roughly a third of their projected capability. But the direction of travel is clear and the pace of improvement is accelerating. One question that looms over all of this is safety. Autonomous systems operating in close proximity to children, elderly individuals, and people with medical vulnerabilities introduce a category of risk that doesn't have easy answers. Tesla's rental-first strategy appears designed in part to address this, keeping tight operational oversight while collecting the data needed to build genuine confidence in the system's real-world behavior. Whether that will be sufficient to satisfy regulators, insurers, and the public at large remains to be seen. Musk has pushed back against dystopian framings of humanoid robotics, invoking science fiction's more benevolent robot archetypes rather than its villains. The honest answer is that neither the optimistic nor the pessimistic extreme captures what's actually being built. What's being built is a complex, AI-driven physical system with enormous potential utility and non-trivial risks. And the decisions made over the next several years about how it's deployed, governed, and improved will matter enormously. The technology is arriving. The question of how society receives and manages it is just beginning to be asked seriously.